Okay. So so let's see here. So we're gonna do problem 18. Um, I'll erase that. Okay. So what's the first thing we do? Draw a picture. Okay. All right. So can you guys read that? Is that okay? Is that big enough? Okay. So it says a rectangular page is to contain 42 square inches of printable area. So 42 square inches of printable area. And it says that it has margins. The margins at the top and the bottom of the page are each 1 inch. Okay, so let's draw a page. And it's going to have 1 inch margins at the top and the bottom. And then one side margin is 1 inch and the other side margin is 2 inches. So let's just say that the right side margin would be 1 and then the left side margin would be 2. Okay, so if I just kind of outline the margins here, it's kind of going to look like this, just roughly like that. Right? So this is 2 on the side here, 1 on this side, and then 1 at the top, and then 1 at the bottom. Does that make sense? Mm-hmm. Yeah? Okay. So that's the situation. And then the question is, what should the dimensions of the page be so that the least amount of paper is used? Okay, so we want to use the least amount of paper. Least amount of paper. Okay. All right, so there's our picture. So we have 42 square inches of printable area. We have our margins that we need. And then the least amount of paper. Okay, so then what's our next step? Yeah, we do need a label. We need to label something so that we can write down the formula, right? So, as usual, you have choices. So the length and the width are different sizes, right? So they need to be different variables, x and y. Sound reasonable? Mm-hmm. Okay. But then the choices are, you can either do something like this. For example, you can say, okay, well, I'm going to let this be x and y, like that. Or you can say, meaning the printable area, right? The red area. Or you can say the entire sheet is x and y. Does that make sense? So it's kind of up to you. You can get to the right answer either way, but you need to pick one. So it's kind of like the wire problem that we did last time. You know, you can do this or that. In the end, you should get the same number regardless. So what do you prefer? Do you guys want to do x and y as the printable area or x and y as the whole sheet? Raise your hand for printable. Raise your hand for whole sheet. Okay, so printable wins. And if you feel like doing it the other way, you can, and then you can compare. Okay. All right, so very important step. The second step is very important. Okay, so this was step 1, right? Okay, now step 2. So step 2 is to write down a formula for the function we are trying to optimize, right? So what is it that we're trying to optimize? Area, right? So we want to use the least amount of paper, right? Least amount of paper. That's what we're trying to optimize. Least amount of paper. And how would we measure amount of paper? It would be by area, right? Does that make sense? Yeah? Okay. So let's see here. So if I write that down, so my area is going to be a function of x and y. Do you guys agree? So what would be the area? Mm-mm. Nope. X plus 3. Exactly. X plus 3 times y plus 2. Does everybody see why it's x plus 3 and y plus 2? Because what is it that we're... So make sure that it's clear what it is that we're looking at. So we want to use the least amount of paper, right? Which in my picture is, the paper is the black outline, right? You guys agree? And the red is the printable area, and that is a constant, right? We know that it has to be 42 square inches, right? So can you optimize the printable area? Well, no, because you need 42 square inches of printable area. It's not going to change. Now, because we labeled x is the width of the printable area, the red, and then y is the length of the printable area, the red, then you have to add the margins, basically, right?
So
Does that make sense?
Chosen it on the outside as the black instead, we wouldn't have had to add the margin.
Exactly, yes. So, right, so if you would have done this, right, if this was y and this was x, like I showed earlier, then your area formula at this point would be x times y. Now that might seem easier, but then it would be complicated later. But it doesn't really matter. It's because it's not complicated either way. So it's just different, really. It's all it is. Okay. All right. Now, after we have that, what do we do? Yeah, you use your constraint, right, to solve for one of the two variables, so that you can write it as a function of one variable. So what is your constraint in this case?
42.
Yeah, the 42, right? So you know that you need 42 square inches of printable area. So, okay. So let's write this down then. So what would that be? What would that look like?
42 equals x plus 3 times y plus 2.
Mm-mm. What is the 42? 42 is...
So would you have to subtract the margin from the 42 or not?
No. So what's happening is you guys are confusing the two different options of labeling. So the 42, this 42 right here, represents this area right here, right? This area in here should be 42 square inches. Do you guys agree? That's what we're talking about when we say 42 square inches. So
X times y.
exactly. 42 should equal to x times y. Again, with this labeling, right? If we would have labeled it the other way, then... So I don't know if this confuses more or less, but the 42 in this case would be... It would be x minus 3 times y minus 2. Does that make sense? Like, that's what it would have looked like. So, so notice it's not very different either way, right? I probably would say that the choice that you made is the better choice. Slightly less complicated. Okay, so any questions so far? Is that okay? Does that make sense? Yeah, not too bad, right? Okay, so then after that, then what do we do?
Solve the
Oh, yeah, right. So, yeah, we're not at step 4 yet. So, do you guys want to solve for x or y? X, okay. So, x is 42 over y. So then, let's write down here the, okay. So then the area as a function of, so if I plug in this x here into there, it's going to be a function of just y, right? So this is going to be 42 over y plus 3 times y plus 2. And I guess I'll write it down up here. Yeah, I might as well distribute it, no? What do you guys think? So if I distribute this, what would I get? I would get 42 plus 84 over y, right? And then plus 3y plus 6. It'll be a little bit easier to get the derivative that way. So, and you don't have to, but yeah. Okay, so 84 over y plus 3y and then plus 48, right? Okay, so any questions up to now? So what's the next step? Yeah, then do optimize, right? So get the derivative, critical points, all that jazz. So a prime of y would be what? What's the derivative of 84 over y? Mm-hmm. Negative 84 over y squared, right? Okay, and then plus 3, right? Okay, good. And then set this equal to 0, right? And solve. So let's see, what would we do? Multiply through by y squared, so you would get minus 84 plus 3y squared equals to 0, right? If you just multiply both sides by y squared. Okay. And then so what would y squared be? 84 divided by 3? What's 84 divided by 3? 28, yep. So y is equal to plus or minus square root of 28. Well, do I need to write down both? No, right? Y can't be negative, right? Because we're talking about the length of a piece of paper, so obviously it can't be negative. The other thing is we did not, so this is one of our critical points, right? But we didn't write down, we skipped one. Did you guys notice? What's another critical point? From the very beginning right there. Yeah, 0, right? But notice we just kind of skipped it. Why is that? Yeah, again, it can't equal to 0, right? It wouldn't be a piece of paper. So, so sometimes, even though it's a critical point, you maybe just ignore it anyways because it's not relevant. It's not in the domain, right, of your function. So speaking of domain, well, what is the domain? We probably should have written it down from the beginning. What's the smallest that y can be?
Close to 0.
0, but not, it can't equal to 0, right? And then what's the largest it can possibly be?
41.
Almost, because y is it's the length of the printable area. So, and you need the margins, right? So it would be 21 minus the margins, right? So 19. Right? Is that right or no?
Why was it 21?
Because
Almost all of it? Almost all the 42?
42 squared. Yeah. Sorry, no, you're right. Wait, hold on. So here, so let's go back. So we're talking about this right here, right? So y is the largest when x is what? Y is the largest when x is the smallest. Exactly. What's the smallest x can get?
Close to 0.
How close can it get to 0? Infinitely close to 0, right? Okay. So this is actually can go to infinity, right? I mean, it would be silly to do so, but because remember, go back to what x is equal to. It's right here, right? X is equal to 42 over y. So as that y goes to 0, x just keeps getting bigger and bigger and bigger and bigger, right? Okay. So it's not a big deal. What is this? What's the only thing that this means?
Can't be negative, obviously.
No. Well, yeah, it can be negative, but it's not a closed interval, right? So then when we're finding the, in this case, the minimum, what are we going to use? Yeah, well, the critical point, but are we going to do the first derivative test, or are we do the, what do we call it? Critical point?
Critical interval.
CIT? Closed interval test? Is that what we called it? So, we're just going to do the first derivative test, right? First derivative test on square root of 28, right? So we ignore 0, we ignore minus root 28, and we're just going to do the first derivative test on positive root 28 just to make sure that it actually is a minimum. Does that make sense? And actually here on the left side I should put 0. Okay, so what would be a good test point? 1. Excellent choice. What about over here? Which one?
Solve for x to do that. You have y. What do you want?
No, we're just going to plug it into the derivative, which is up here in the block. We're just going to plug it into here, right? Because all we're looking for is the sign. Is it positive or negative? So let's see. So what would be a good test point? 6 is okay. You're going to square it. So notice you're going to plug it in right there, right? So maybe, 6 is fine, but 10 is better, right? Because then you'll have 100 on the bottom, so it's nice to work with, you know? Don't you think? Again, these are all just kind of personal preference choices. It doesn't really matter. But okay, what happens when I plug in 1? I get minus 84 plus 3, which is a negative number, right? So what does that tell me? That means that it's decreasing, which is exactly what I expected, right? And then if I plug in 10, what do I get? I get minus 84 over 100 plus 3. What is that? That's a positive number, right? Minus 84 over 100, that's less than 1, so then it's going to be a positive number. So then it's increasing, right? Okay, so then what does that tell me? That tells me that this is the minimum, right? So but notice this does not really necessarily answer the question. So the question said, what are the dimensions that use the least amount of paper, right? All this is in this case the y value that gives me the least amount of paper, that uses the least amount of paper. So, go ahead.
Oh no, but then you can just plug it back into the equation to solve for x.
Yes, you just have to make sure that you're looking at the right thing. right? So, for example, the answer to the question. So let me let's see. I'm trying to see what I can erase here. I'm gonna put it right here. In this little. I'm gonna make a little cubby. I'll do it right here. Okay, the answer. Okay, so the dimensions are, let's see, I'm going to call it the bottom and the side. Okay, so what's the length of the side? So this side that minimizes the area. Root 28 plus 2, right? So make sure you don't just grab the number root 28 and then I'm done. It depends on what it represents. So notice this, the y, this is root 28, right? So then the whole side of the piece of paper would be root 28 plus 2, right? And then what about the bottom? What would the bottom be? Well, it would be x plus 3, right? Basically. And then what's x? Remember, x is from right here. X was 42 divided by y, right? So then it would just be 42 over root 28 and then plus 3.
So 10.94.
Yeah, whatever that is. Does that make sense? Yeah? Yeah, so the main thing is, just make sure that you're answering the actual question that's being asked, right? So don't just grab the number and be like, oh, okay, well, that's the answer. I'm done. So make sure you go back and you answer the actual question itself. All right, so questions? Yes?
I'm confused. Why is it root 28 plus 2?
Because remember, root 28 is y, which is this side right here.
Right.
Okay, but the question is, what are the dimensions of the paper, which is the whole thing, including the margin?
Oh.
So that's why you need to just add the margin.
Which is 1 and 1.
Right, one on the bottom, one on the top, so then you add 2. Yep. Any other questions? Yeah.
I get why you got infinity in domain, but I don't understand still why.
No, I do get what you're asking. Well, it's just because theoretically, kind of like in the fence problem where we said the fence could theoretically be as long as we wanted it, even though it's infeasible. It's the same thing here. The length of one side of the printable area theoretically is infinitely long. It's possible to be infinitely long, even though practically it can't actually be. But for example, I mean, if you, let's just say for the sake of argument, you stretch this out to 42. Okay. That. What is that? I mean, I just put a bunch of zeros there, but that's million, billion, trillion. So you make one side 42 trillion inches. Okay, well, you can still get the area to be 42 square inches. What would you need? So that's the length, right? If the width is 1 over a trillion, isn't that 42 square inches of area? I mean, it's ridiculous, right? But theoretically, that it's possible. So that's why you can just keep extending one of the sides forever and then just adjust the other side to make the same amount of area. Any other questions? Fun times, right? Okay. All right, let's do another one. Fun times with optimizations. Oh wait, no, I don't. Hold on. Okay. All right, so we're gonna do the rowboat problem. Are you guys ready? Okay, so it says, ignore the circle picture. That's for a different problem. So this is number 58. So it says that a man is floating in a rowboat 1 mile from the straight shoreline of a large lake. Okay, so here, I'll just redraw the picture over here. So here's the shoreline. And then here's the rowboat. And then this is 1 mile. 1 mile, like that. And then you have a town over here. Town. So a town's located on the shoreline 1 mile from the point on the shoreline closest to the man. So this right here is 1 mile. Actually, I'm going to put it over here. 1 mile. Okay, so here's P. And, okay, so there's 2 parts. So, to what point should he row in order to reach his destination in the least time if he can walk 5 miles an hour and row 3 miles an hour? And if he can walk 5 miles an hour and row 4 miles an hour. Okay, all right, so that's our problem. Okay, so all right, so any questions about the setup of the problem? Anything? Or are we doing okay so far? So let me just kind of redraw here a little bit. So here's the town. Okay, so let's do this first one. So walk 5 miles an hour and row 3 miles an hour. What do you guys think? What should we do? Label things. Okay, so we need some variables in here, right? So we have the 1 and we have this other 1 here. So we have 1, 1. It's not really to scale, is it? But oh well, that's fine. So 1, 1. So what variables do you guys want to put on here? What do you guys think? D. So this right here, D. Okay, that's fine. What else? Is that the only variable in this whole thing?
No, from P to the town.
P to the town, or P to this spot right here, right? So either one. So it doesn't really matter. Why don't we do, let's say this is X right here. So X is this distance right here from P to the horizontal distance from the rowboat to P. And then what would this distance be from the town to P? You could call it another variable, but it's much easier to call it 1 minus X, right? Right, because the distance from this point here to the town, that's 1. So then that would just be 1 minus X. Okay, so so any questions so far? We doing okay? Yes? So?
So you labeled X the whole 1 mile or just from 1 to P?
For X is from this point, let's see, Well, maybe we should call it something else. Maybe A. A from point A to P is X. Yeah. Okay, so what else? So now we need to write down a formula. What are we trying to optimize? Mm-mm. No, what did the question say? We want to
Oh, the least amount of time.
least amount of time, right? So we're trying to optimize time. So so this is time to town, TTT. All right, well, what would be the time that it takes us to get to town? Well, if you think about it just if you take baby steps, do you guys agree that it would be, you can say that this is, let me do it this way, time rowing plus time walking. You guys agree? Okay. Now, how would you find the time rowing or the time walking? What do you need to know to find either of those? Think of a formula that was drilled into your head over the course of many, many years throughout your early learning careers. Distance equals rate times time, right? So distance equals rate times time. Dirt. So if distance equals rate times time, d equals rt, then t equals to d over r, right? Distance over the rate. Okay, so that's how we're going to find the different times. So what's the time spent rowing? What would that be? So it's distance rowing divided by rate rowing. So what would be the distance spent rowing?
1 mile.
D, right?
Capital D.
Capital D, because that's the distance rowing, right? That's this in the red that we labeled D. Maybe I'll label D in red. Okay, divided by what?
3 miles.
The rate rowing. So in this case, it's 3. Why is it 3? That's because the rate rowing is 3 for part A, right? Later on, we'll change that to 4 and see if that changes anything. Okay, and then plus the time spent walking. So what would that be? What's the distance spent walking? 1 minus x. Yep. And then that divided by 5, right? Because that's the rate walk that you can walk at. Does that make sense? Okay, so how are we doing there? So not quite one variable yet, right? So what can we do to write this in as a function of one variable? Use the Pythagorean theorem to solve for D, right? Okay, so if I use the Pythagorean theorem here, so I can say that D is equal to the square root of what? 1 plus x squared, right? Or x squared plus 1. So, all right, so then this is my function. T is equal to the square root of x squared plus 1 over 3 plus 1 minus x over 5. Okay, so any questions up to that point? So this does not look like a very nice function, but we at least were able to get a function reasonably well. So any questions up to this point? Are we clear on where we're headed? So, no? Okay. All right. I'm going to write this in a new page because we're going to run out of space for sure. So let's do the next step over here. So we have square root of x squared plus 1 over 3 plus 1 minus x over 5. Okay. All right. So then what do we do? Derivative. Good. So derivative is equal to... So the derivative of square root of x squared plus 1. What is that? 1 over
2 times the square root of x squared plus 2.
and then I'll just leave the 3 down there like that. And then times the derivative of x squared plus 1, which is 2x, right? Yeah? Okay. And then notice the 2's cancel, right? So that's nice. Okay, now plus the derivative of 1 minus x over 5. What is that? What is it? 1/5, right? Well, minus 1/5. Right? The derivative of minus x is just minus 1 over 5, because 5 is a constant. Okay. And then what do I do? I set this equal to 0 and solve. So now when I'm finding my critical points, notice, do I get any critical points from the denominator here? Can x squared plus 1 equal to 0? No, right? So we can safely ignore that. So then let's set it up here. Let's see. We have x over 3 square root of x squared plus 1 is equal to 1/5, right? If we move the 1/5 over, the minus 1/5 over. And to relive our algebra youth, we can cross multiply. You guys remember that? Doing those kinds of shenanigans. Just for fun. Okay, and then what? Then what do I do? Well, no point turning it back into fractions again. What about squaring both sides? Yeah? Okay, so if I square both sides, I would get 25x squared is 9x squared plus what? 9x squared plus? Well, it depends. Let's say we're going to get rid of the parentheses. 9x squared plus 9x squared plus 3, right? You sure? It's 9, right? X squared plus 1 in the parentheses, but you distribute the 9, so then... Yes? No? No? You guys are looking at me funny. Okay. I'll leave the 1 there. Right? So you square the 3, you get 9, and then x squared plus 1. Okay. Okay, so is it okay if I go back to 9x squared plus 9? Okay. All right, so now what? So 25x squared minus 9x squared. What is that? If I move the 9. There we go. 16x squared equals to 9. So x squared is 9 over 16. So x is equal to 3 over 4. Now is it plus or minus? Technically yes, right? But we throw out the minus because it has to be positive, right? If we go back to our picture, obviously x, which represents the distance, cannot be negative, right? Okay. All right, now question. Should I... So this is my, in this case, one and only critical point, right? So should I... oh, geez. Okay. Should I do the... what's it called? The first derivative test as my next step? No. Excellent job there. We're going to use the closed interval test. Why is that? We just called it closed interval test. It's not really called that. But why is it? Because we have a closed interval in this case, right? So if I take a look at my domain here, what's the smallest x can possibly be?
1.
No, smallest.
Real close to 0.
Nope. Isn't the domain, doesn't it start at exactly at 0? Because what would it mean for x to equal to 0?
It wasn't a triangle.
Right, it's not a triangle. But that just means that you just row straight across immediately to A, right? Just go straight across and then walk the entire 1 mile, right? That's what it means for x to equal to 0. So this right here is row to A and walk 1 mile, right? That's one of the endpoints. What would be the other endpoint? It would be 1, right? And what does that correspond to? This is if you row straight to town, right? Straight to town. And not walk. And what's the other option? Somewhere in between, right? Which is exactly what we're looking for. We're looking for, well, what's the optimum point to row to? Well, it could be somewhere in between, but it could very, very likely also be one of the two endpoints, right? Does that make sense? Okay. So, all right. So why don't we just do it right here? So what are we going to do? We're going to figure out what the. No, actually, we probably don't have enough space. Okay. So we're going to look for the time at 0, time at 1, and the time at 3/4. Does that make sense? And we're going to compare the 3 times. Notice, do we need to do the first derivative test at all? No, right? Because if you have a closed interval, you don't need to do the first derivative test. You can if you feel like it, but there's no point really in doing it because you're looking really for the absolute, in this case, minimum, right? You're looking for the absolute extrema. So doing the first derivative test really is only needed when you have an open interval and you can't actually plug in the endpoints. Does that make sense? Yeah? Okay. All right. So what do I get when I plug in 0? So here, the time function's right here. So I plug in 0, I get, what is that? 1/3 plus 1/5. So what is that about? .53? Okay. If I plug in 1, what do I get? √2/3 plus 0, right? So what is that? 0.47. Okay. All right, and then last but not least, 3/4. So that would be, let's see, the square root of 3/4 squareds, right? So 9/16 plus 1 over 3 plus, let's see, 1 minus 3/4. So it'd be 1 over 20. So what is that?
0.466.
This would be 5/4, right? Well, so this would be 5/12, right? Plus 1/20. What'd you get there? How many?
7/15.
0.466 repeating.
Yeah, 0.466. 0.466. So let's say. So which one's the minimum? 3/4, right? So this is the minimum. So the minimum is when x is 3/4, meaning if we go back to our picture, if you row whatever distance that is, right? If you calculate using the Pythagorean theorem, so the minimum for part A, the minimum is when you walk 1 minus 3/4, right? So you walk 1/4 of a mile, and then you row. What is that? The square root of 9/16 plus 1, right? Because this is big D, right? So that would be 5/4 of a mile that we row. Does that make sense? Okay. So notice that one was at the critical point, right? But so just thinking a little bit, without going through all the work here, how would part B change, hypothetically? We're rowing faster, which means that instead of being P being here, where is the optimum spot going to be moved to? To the closer to town or further away from town? If you can row closer to town, right? Because you can row faster than you can walk, so it's probably going to be better to row closer to town. But do you know if it's faster to row straight into town versus a little bit before or a little bit after? You're not sure, right? You need to figure out. So let's try to go back here. So why don't we do this? We don't want to go through absolutely everything, but if we just look at the relevant parts here, where are they? It's this 3, right? That 3 would be a 4, right? So everything else, everything kind of is the same here, except that 3 is going to be a 4. So then this, let's see. So what's going to, this 9 is going to be what? So 4, 4, 4, 4. That's going to be 16, 16, right? Okay. So then if I subtract 16x squared here, I'm going to get 9x squared equals to 16, right? Okay. So now what is x squared equal to? 16 over 9, right? So x is going to be 4 over 3. Okay. All right. So question. So this is my critical point, right? If I can row 4 miles an hour, my critical point now turns into 4 over 3, right? So we imagine we went through all the steps, which we didn't really need to because we already did everything. We just changed all the numbers. So do I do the same thing and do this and compare that to the other ones? Exactly. It's outside of the domain. What does that tell you? That it's way faster to row straight into town. Exactly. Does that make sense? So the critical point that you found puts you rowing not to town, but it puts you rowing past town. So, but that's because when you're doing the calculus, you were given a function and you're not bounded by, meaning the function itself is not bounded between 0 and 1. It's the problem itself, the problem itself, meaning that the what you're trying to optimize, the going to town, all that stuff. So, this function that we're looking at here, this time function, this really knows nothing about the town and there's a boat or anything like that, right? This is just a function that you're trying to optimize. So the minimum of this function, when you put in the 4s and whatnot, is when x is 4/3. But now if you go back to the context, in the context of your problem, 4/3 is not in consideration, right? Because it's outside of your domain, because you would be rowing past town, and you don't want to row past town because it's faster to row straight to town at that point, right? Does that make sense? So what this tells you is that, so when is it the minimum? Or let's say time is minimized by rowing straight to town, right? Straight to town. In that case, right? Does that make sense? Fun times, right? Fun times. So yeah, I mean, fun. You guys want to take a break?
I'm confused on the.
Okay, go ahead.
So we found the critical point, and then the test points before and after.
Yep.
For the absolute. But why are we?
Well, remember you test the endpoints and the critical points.
Oh, that's right.
Yeah.
What are the endpoints?
Yep.
It's enclosed.
Yep. Yeah, that's why earlier we said the domain. We wrote it down on the other sheet, but the domain is from 0 to 1, right?